Hello everyone. Today I'm presenting applying the transformer to character level transduction. This is a joint work with Ryan and Mans. So this project originally started in early 2019, and transformer back then already dominated most NLP tasks. Yet for many character level sequence-to-sequence tasks, LSTM was still the state of the art. For example, on morphological inflection share tasks or historical text normalization. And for character level transduction tasks, the training set usually contains only around tens of thousands of examples. So as a result, it's much smaller compared to machine translation or self-supervised learning. So in this project, we are wondering whether transformer can perform as well as LSTM or even better. And so first we conduct an application study with morphological inflection. We select 5 languages based on the performance on the previous share task. So here, the 5 languages will be the most challenging languages. Due to the data size, we will be using a smaller transformer with only 4 layers and 256 hidden size. As a result, our transformer model would have a similar number of parameters as the LSTM baseline. And so first, we look at the input encoding of transformer. So in feature-guided transduction, the features are usually a set. And here we present an example using morphological inflection. And the order of the feature should not matter. However, in the vanilla transformer input encoding, as we can see in the top half of the figure here, it differentiates different features in an arbitrary ordering. So here we propose a feature invariant encoding by using the same position for all the features. And additionally, we would have a type embedding to differentiate between the feature and the character, as shown in the bottom half of the figure here. So as a result, the ordering of the feature would not matter in the feature invariant encoding. And then we look at the training strategy of transformer. So first we look at batch size. Here we run a control experiment against between the LSTM-based model and the transformer-based model by using the same learning rate scheduler. So here we warm up the learning rate linearly and then decreasingly to 0. As we can notice in this figure, the transformer-based model only starting to outperform the LSTM baseline when it used a large enough batch size. So here, the training set was only 10,000. So a batch size of 400 would mean only 25 updates per epoch. So this batch size is relatively big with respect to the data set. And here we also notice that our feature invariant encoding outperformed the vanilla input encoding. And then we look at the label smoothing of transformer. As did the original transformer paper, we also confirmed that using a small label smoothing improves the transformer performances. And also using non-default beta 2 for Atom also lead to a small performance gain. And here we can also notice that the feature invariant encoding consistently outperformed the vanilla encoding transformer. So taking everything we learned in the evaluation study, we put together a transformer with our input invariant encoding. We use a relatively large batch size of 400 and label smoothing of 0.1, and finally beta 2 for Atom of 0.98. And in the evaluation, we consider 4 character level transduction tasks. First was the sigma-form share task of 2017 on morphological inflection, and this task was a feature-guided task. And then we look at the historical text normalization, and then the grapheme-to-phoneme, and finally transliteration. And so let's first look at the result on morphological inflection share task. Here it covers 52 languages. And we found that the our transformer model outperform all the model in the literature, even without using any ensemble. So here we establish a new state of the art. And then we look at the historical text normalization, which cover 6 languages. And again, we show that the transformer also outperform all the models in the literature. Again, establishing a new state of the art. And then we look at the result on grapheme-to-phoneme on English and transliteration on 14 language pairs. And again, here, the transformer-based model also outperform a strong LSTM baseline. And finally, we take a look at the error that made by the LSTM and the transformer on morphological inflection. Here we plot the number of error versus the inflected form length. And we can see that the transformer model considerably outperformed the LSTM model in most of the range, except the really long inflected form. And in that long tail, both models make roughly the same amount of error. And that concludes our talk. Thank you. And you can find the code in the following URL.